everyone, I'm Kiara McKenney, and on behalf of the Applied Technology Council, I'd like to welcome you to this webinar on FEMA P-2091, a practical guide to soil structure interaction. This webinar is brought to you by the Applied Technology Council under a contract with the Federal Emergency Management Agency. If you haven't already, you can download the handouts using the link in the chat. I do see some reports that the link may not be working for everyone, I think because this is a very popular webinar and everyone's clicking on the same link. But the PDFs that are being issued in the chat are identical to what's at that link. So go ahead and download them through the PDFs if you are having issues accessing that link that was sent out. So we know that many of you are interested in receiving professional development hours for your attendance today. For those who registered and attend the webinar, a certificate documenting PDHs will be sent by email within 4 weeks. If at any time during the webinar you have questions, please go ahead and type them in the Q&A. We will not be having a live question and answer session during this webinar, but we will provide all registered participants with written responses to the technical questions we receive. I would now like to turn it over to Patia Scott from FEMA's Earthquake and Wind Programs branch, who will provide a brief introduction to today's webinar. Patia, please go ahead.
Thanks, Kiara. Good afternoon. My name is Patia Scott, and I'm a civil engineer for the Federal Emergency Management Agency's Earthquake and Wind Programs branch. It's a mouthful. It's my pleasure to welcome you to today's training in one of our newer publications, FEMA P-2091, a practical guide to soil structure interaction. As part of our responsibilities under the National Earthquake Hazards Reduction Program, FEMA supports activities to reduce future earthquake losses. The primary way we do this is through the development and publication of technical design and construction guidance products, as well as through the support of training and related outreach efforts such as this training. FEMA supported and worked with Applied Technology Council to develop this training course, and I want to add a big thank you to the project team that worked on this new highly useful publication and training. They put together really great guidance in spite of a few hitches on our end. So as the title suggests, this provides information for design professionals on using the soil structure interactions requirements in ASCE, SEI 7, and building code. So we hope you enjoy this webinar. Back to you, Kiara.
Thank you, Patia. Thank you, Patia. So now let me tell you about your incredibly accomplished presenter today. Brett Lazundia is a structural engineer and executive principal at Rutherford and Chakeen in San Francisco. He has over 30 years of experience in structural design of new buildings, seismic evaluation and rehabilitation of existing buildings, peer review and plan checking, and applied research and guideline development. He was project manager and co-author of FEMA 547, Techniques for Seismic Rehabilitation of Existing Buildings, a co-author of FEMA 306 and 307, Evaluation of Earthquake Damaged Concrete and Masonry Wall Buildings, project technical director for the 3rd edition update to FEMA P-154, Rapid Visual Screening of Buildings for Potential Seismic Hazards, the project technical director for the publication of FEMA P-2006, Example Application Guide for ASCE 41, and the project technical director of the ATC 144 project that led to FEMA P-2991, which is the subject of today's webinar. He's a past president of the Applied Technology Council and the Structural Engineer Association of Northern California. We're so happy to have him here today to help make soil structure interaction more approachable to everyone in the audience. Now I'd like to go ahead and turn the webinar over to Brett. Brett, please go ahead.
Okay, great. So are you able to hear me?
Yes.
Good, good. Well, welcome everyone. We are broadcasting here from a beautiful day in Northern California. And of course, what else would you do on such a day but talk about soil structure interaction? So hopefully we'll have something worthwhile and interesting for you to learn about over the next 90 minutes. So I want to give you a little bit of a taste of what the outline of the presentation is. Soil structure interaction, like a lot of things in structural engineering, has jargon, and you kind of have to know it in order to really even be able to follow the building code provisions or just even follow this talk. So we'll start with that. There's different ways you can model how the soil and the structure interact with different levels of sophistication. I'll kind of explain a couple of kind of two ends of the spectrum, and we're going to be doing the simpler one. We'll talk about when SSI is important and when it's not, ways that you can quantitatively figure out how likely it is to be of significance for one portion of SSI, what we call inertial effects. We'll list the topics that are covered by ASCE 7 as well as ASCE 41. We'll have a few examples on 2 kinematic interaction SSI techniques, base lab averaging and embedment effects. Go over an example of how different ways that you can model a building with a basement. Comes up. I'm sure many of you have already done that. You can see it, how what you've done compares with what we're suggesting. We'll have a couple of detailed case study examples at the end. Only a taste of those. There's a lot in them, and the guide itself has much more than we can cover today, but we'll give you a sense of what's there, and I'll wrap up with some tips on how how to best understand SSI and implement it, just kind of things to walk away with, hopefully that stick with you. So our goals, I want you to have a better familiarity with the terms and what they mean, when this would matter and when it doesn't. This is not something, that you do very frequently, and we don't want you to waste time doing it when it's not going to help you. I want you to understand how it changes things. It can do a variety of things, and it's important to kind of understand those at a high level. We'll apply it to some different building types to get a sense of that, and then learn kind of where to go for more information. So we wanted to ask a couple of questions, so we'll have a few scattered throughout some polls. So Kiara.
Great. So if you are a practicing structural engineer, please tell us, have you used soil structure interaction in new building or retrofit design? And if you are a practicing geotech, have you provided soil structure interaction recommendations in a geotechnical report? So you can say never, 1 or 2 times, or you're very experienced 3 or more times. So we're looking at the responses come in. This seems like at least it's an easy one. So I'm going to leave the poll open for another couple seconds. So go ahead and get your answers in. All right. Okay, I'm going to go ahead and close the poll. I am sharing the results, Brett.
Great, thank you. Okay, so let's talk about the first one. So for those of you who are structural engineers, which looks like a lot of our crowd here. So, of nearly 1,000 people, almost, 850 are civil or structural engineers, and a fairly substantial number of you, 200, 139 people have done this. So we're talking to a group that ranges from, haven't used this to have done it. That's good. Our target audience for the document is intended to cover both groups of people, and I can see that of the geotechnical engineers in the crowd, it's great that we have some. This is obviously a nexus where structural engineers and geotechnical engineers need to come together, and we can see that there have been people who have provided recommendations, a fairly substantial number. So again, nice split, it sounds like, in the crowd. So I'll sort of bear that in mind as I go forward. All right, so let's talk some terminology. These pictures began in a NIST document, goes by the really memorable name of GCR 12-1721. It's just the numbering scheme that NIST uses in their documents. That was an ATC 83 project. I'll show you a cover of that in a minute, but that was a great compilation of useful information a few years back, but it remains kind of the best thing out there. So these images have been adapted from those. So we've got a building on the left that's wiggling around, the ground motion, UG there. I didn't ask, Kiara, do you see my cursor at your end?
I do. Yes, I see it.
So, we're wiggling the free field motion of the ground, and the building feels something that comes into its foundation. So that's often called FIM, F-I-M, the foundation input motion of what the building is actually experiencing, since that's somewhat different than the free field motion. And that difference is caused by kinematic interaction, and we'll explore that in some detail. That's kind of half of the story. The other half of the story is what's called inertial interaction, which is a little more complicated and involves damping of the soil. There are several different kinds of damping, and essentially the interaction of that whole dynamic system of masses and dampers and springs and how they go together can be parsed out into inertial effects, and we'll cover several of those today. So in more precise language, free field motion, that's what a strong motion instrument might record. USGS and many other entities, California Geologic Society in California, has sensors on top of the ground, and they record them, and you can go onto their websites and see what happened in an earthquake. They also have ones in the building, but the UG there are those free field sensors. Foundation input motion, that's what effectively excites the building. So that translation of what is the base of that building really feeling. And kinematic SSI is that term. That's what is doing the modification. And there's two main kinematic interaction effects. One is called base slab averaging, which is where a shallow foundation is experiencing different waves over its full footprint. And yet the foundation, if it's linked together, which you need to have base slab averaging, it sort of smooths them all out, because things come in from this side, they come in from that side, but the foundation being linked together sort of averages them all out. So the highs kind of go away as a result of that. And it has effects that are dependent on the period of response. Another thing that does this is deeper embedments can change the way the building feels motion as well. And essentially, the deeper you are, the more reduction there is, but it's fairly specific in how things change, and we'll show you that in some detail. So that second half of the story, that inertial soil structure interaction effects, we've got several. So one has to do with period lengthening. So if we fix the bottom of a building, like the most simplest model, a fixed base model, then that will be our stiffest, shortest period building. If we account for the flexibility of the soil, and we put something that allows for that, a spring, for example, then we're typically going to increase the building's period. It's going to lengthen, it's going to drift more, and that can do a variety of things. There's a couple different kinds of damping. Just like there's damping, equivalent viscous damping in the structure that we're kind of all familiar with probably, there are damping effects in the soil. So soil damping is one. Soil damping is hysteretic damping. That's what's most similar to viscous damping in the building itself. Radiation damping, has to do with how that soil structure interaction and the propagation of waves, to and from the foundation, and it's related to how things are moving in the ground. And those in the building code, they're actually separated into two different processes and sets of equations, and you can add them together. So it's always good in any document to have scope, who's our target audience, and who's our purpose. So I wanted to kind of highlight those for you, just to sort of explain where this is coming from, which I think is exactly this group that we have from our first two polling questions. So the scope, we're covering all the sort of main SSI topics that are in ASCE 7 and ASCE 41. So you can see the list there. We have an easy to use rule of thumb on when the inertial portion of SSI is likely to be of significance. That came from that NIST document, but we've kind of adapted it and refined it and made it a little more clear on how to use it. As I mentioned, we have advice on basements, both in flat sites and sloping sites. Our focus here, though, is on practicing engineers. The NIST document that preceded this was a little more academic, kind of a compilation of many different things, a little more research focused. This is not that. This is hopefully something that a practicing engineer can turn to and easily get, clear, helpful advice that then can help them do this in their everyday practice. So we're using springs rather than finite element modeling, for example, and I'll show you a little bit of that in a minute. So direct analysis is the term that in the SSI world that's used for finite element modeling. So you can see this picture on the left, and this might be done in a nuclear power plant or an important underground subway line where there's a lot at stake and there's a lot of resources to do this. And the soil itself is modeled with finite elements, just like the building is modeled, and there's an interface between those two that's very special, and then waves are put into this system, and you look for the response of the soil as well as the building, and trying to understand how it changes. This is obviously a lot of work, and kind of an art, and not a lot of people do this or are skilled at doing it, and it's not something that in today's current environment is something I would consider the practicing engineer like me would ever do, frankly. What we would typically do is what's on the right, is that we would put a spring underneath a column or underneath a spread footing, and it could be a vertical spring, could be a horizontal spring, could be both. This is called the substructure approach method instead of the direct analysis approach. So this whole guide and all the provisions in the building code, they're all about the picture on the right. How to use springs and what do springs do, and there's no need to have finite element modeling of the soil. So second thing is, what's the purpose? We want to kind of educate practicing engineers on knowing when it would be beneficial, or at least worth checking to see if SSI would be of value, and when it wouldn't be. And then we want to show you examples, worked examples of different SSI techniques with equations, with advice, with commentary, with, why do it this way? Where does this come from? What's behind it? How do you do it? And lots of pictures. So it's not a series of equations without anything else. It's those plus all that other stuff. So our target audience, we're assuming that you are familiar with seismic design. So, this is not a guide to teach you how to do seismic design. The presumption is you've done that before, but we're not assuming you have much or any, frankly, experience with SSI. On the other hand, if you have done it, and maybe you've done one technique, or, and maybe without even realizing it, what it was called in the SSI world, and you want more advice and you want to explore it further. So it's for those folks as well. So a lot of really knowledgeable people were involved. The way these tend to be structured, the way the Applied Technology Council's kind of standard approach to things, and what FEMA, NIST, and other agencies like to have is, FEMA is the client, they're hiring ATC. ATC in turn has a project manager, so that was Aisha in this case, and they engage a technical committee who are the primary authors of the document and kind of developers of the information. So we had a diverse group of professors, geotechnical engineers, practicing structural engineers, besides myself. Then there's a review panel of very knowledgeable, experienced, and fairly diverse group as well. And then for selected tasks, we engaged some people to do different things, call those working groups. So there might be a working group focused on this or a working group focused on that, and those folks there on the right were involved in that. So a lot of people, takes a village, so to speak, to do this, and it's an excellent crowd that I'm very thankful that we had. So I mentioned this next document a couple of times. This is it's oh so sexy cover, and on the other hand, there's a lot of really great information. This was led by John Stewart, a professor at UCLA, and one of his graduate students, and then a whole team of other people. I was part of that, but this is a great resource for all kinds of things, including kind of a bit of the background on where many of these provisions come from, and then additional information that goes beyond what's in the building code. It was not directly intended really to be a design guide. It has some examples on it, but they're fairly sophisticated and fairly detailed. So the one we're talking about today, it's kind of a next step. We sort of, in one metaphor, we're, in football terms, we're taking it from the red zone into the end zone, and hopefully we're scoring a touchdown with you folks in our current guide. So that design guide, 10 chapters and 2 big appendices. So those worked examples, these are full building examples in Appendix A and B. And then the chapters leading up to that, they pick off specific topics. So they all have worked examples inside of them as well, but they have, they're focused on one particular SSI technique, for example. So chapter 4 is like all about base slab averaging, but you don't like get this huge discussion of a big building. On the other hand, in Appendix A and B, base slab averaging will be talked about as one of many things, but you'll see it kind of from start to finish of how a structural engineer would initiate and then include implementing different SSI techniques. So all these things in green are in ASCE 716, which is largely unchanged in ASCE 722, which was just released in December. There were some modifications in Chapter 19. Some of them were driven actually by this project, because we made some recommendations about terminology that is not consistent and could be improved. So those were adopted. No real fundamental provision differences between 716 and 722. ASCE 41, for those of you who are familiar with that document, which is sort of the main document for retrofit in the US, that one also has detailed provisions on SSI. They're very similar, but not necessarily identical to those in ASCE 7, and we'll talk about that a little bit. Things in black are not directly in the building code, but are kind of related to that, and hopefully they're of value to you as well. So let's talk about when SSI is likely to be an important effect that actually changes something and matters to you. So the first thing is base slab averaging. Remember that linking of in this case, orthogonal grid of grade beams and spread footings, and kind of averages out all the motions. So you might have motion, coming in on the right side and coming in at left side, and they're likely to be somewhat out of phase. And so the foundation kind of smooths it all out. And one metaphor maybe you could think of as if a building had legs, and that's the foundation, and you had a short person holding up one leg and a tall person holding up another leg, and some medium height people holding up the other two, and they're all, having different strides. So those are like input motions that they're inputting into those table legs, but the table kind of holds them all together, and the table only feels the kind of average of all those things because it has its own stiffness. That's base slab averaging. It has a bigger effect on short period spectral response, and it has essentially no effect on long period. Now I'll show you what we mean by that a little bit later. So deeper means that there is a bigger kinematic interaction embedment effect. So that depth tends to reduce the ground motion that would have been experienced at the free field, but is that foundation input, that FEMA input to the bottom. So deeper embedment, like this building on the left, is going to have a bigger impact and a greater reduction also in its short period spectral response, and pretty much no impact from 1 second beyond. Okay, so let me ask you a question here, or I'll actually let Kiara ask that question.
Great. So for this question, for a given site and a given building height, would you expect soil structure interaction to be more important for a flexible moment frame or for a stiff shear wall building? So we'll leave this open for a few seconds. All right, it looks like most people have answered, but in case you need a couple more seconds to think about it, go ahead and give it your best shot. And I'm going to go ahead and close the poll. Brett, I'm sharing the results.
All right, so this is a little bit like our partisan split in America these days, that we're about half and half. So this is a little bit of a sneaky question on my part. I think the kind of intuitive feel is flexibility must have some bigger impact from flexibility in the soil, and actually it's the other way around. So it's the shear wall. So this is a fairly precise question, even though it may not seem like it. So given site, so I'm assuming the same ground motion goes into both the moment frame and the shear wall, like they're right next to one another, let's say, and the same height. So that H is the same here, but what's different, because the one on the right is stiffer kind of inherently than the one on the left, the period of the one on the right is lower. That's a big deal, and I want to show you kind of one way to think about this. We have situations where SSI is important. We talked about a couple. Here's another one. So when we have a high structure to soil stiffness ratio, okay, so let's parse what that means. High structure to soil stiffness. So that means the structure stiffness to the soil stiffness is high. So a stiff building on flexible soil, that's the shear wall. Okay, so this here is a shear wall, it's a cantilever shear wall. It's got, if we fix the base on the left, then we just have the, bending and shear deformations that happen in this, and there'll be, axial extension in the top corner, and over here on the right, there'll be some downward movement. If we put that on springs to represent the flexibility of the soil that's underneath this rocking or rotating building, then there's going to be some additional movement, right? We're going to have the original delta W of the wall itself, the building, and then we're also going to have some rotation that is the delta F here, that's the uplift and compression of these soil springs. And the amount of total movement with respect to the ground sideways would be delta total. So what this does, the building on the left has a shorter period than the system on the right. That means the period gets longer in this one on the right, and that will automatically mean the displacements are bigger, and its spectral displacements are bigger as well. What it doesn't necessarily mean is that the forces go up, and we'll show you a little bit about why that is actually on this slide. So here's a response spectrum. And so period is on the x-axis, and spectral acceleration, which would be proportional to the base shear, is on the y-axis. So this should look pretty familiar to everybody here. So we start at sort of the equivalent, soil peak ground acceleration at 0 period, and then we dynamically amplify up to the plateau. This sort of traditionally is maybe around a half to 1 second, depends on your site class, of course. But as you get up there, if we have period lengthening. So if we had a really stiff building and we started with that line where my cursor is, and then we moved up because the period got longer, we would actually be climbing up the response spectrum. So the base shear and the forces would go up. Not too common, but definitely possible. A little more common, particularly as the buildings get taller and the periods get longer, is that we're on the downward side. And as we go from the black dot here, T, to this T tilde, which is the with the flexible base, then we get an extension of period and we're going down the response spectrum. There's also a change in damping that can occur. So when you start to look into SSI, you often will be able to take advantage of soil damping, and that can be added to the the viscous damping of the building, and that can lower the overall response spectrum as well. But you can see that that's still not necessarily going to change the fact that there are times when you can go up and there's times when you can go down. But in either case, it matters, right? I mean, there is a change, and it's an important change. Okay, so let's talk a little bit more about things that go up and down and things that rock. This is one of my favorite examples. So this comes from FEMA P-2006. So that was, Kiara mentioned that in the introduction. One of the things I'd been involved in was that document. It's about ASCE. It's a design guide to using ASCE 41. And so there's a lot of things in there. It's a 2-volume thing. It's hopefully super valuable to anybody who wants to use ASCE 41. There is an example where a number of examples, but this one in particular is kind of easy to see. On the top model, this is a classic fix it for vertical and horizontal, let it rotate at the bottom. So these are pins underneath the columns. And if we push this thing sideways and we push it and we push it, eventually something buckles. So this bottom brace, the one in red, is getting hammered, and it's the first thing to go. And that's not a good way to fail. If we instead take the same building, take the same demands, but we put vertical springs in here to represent the flexibility of the soil underneath this and allow it to rock or rotate, then the building actually worked for that particular set of demands. So it wasn't over. It was a blue number here instead of red. Red was bad. Red was sort of a demand capacity or a utilization over 1. So this is pretty dramatic. A simple thing of adding soil vertical springs to permit foundation rocking was able to, show that the building went from being not okay to okay. Now there's a little bit of a price to be paid with rocking, and that can sometimes be a very big deal. So what you can see in the deflected shape is that, yeah, these guys are rocking, but that translates into the beams that connect to the braces. The rotation that they have at that interface is much bigger than it is in the fixed base model. So if you had sort of a non-ductile connection between that beam and the brace, then that could be where you could have a lot of damage. So in an older concrete building, let's say these were shear walls instead of braces, you had beams, then this could be a bad thing. But it's kind of a real thing. The fixed base model, unless you're sitting on rock, and that's not what really happens. This picture on the bottom is much more realistic of what really happens. Okay, so here's an example of what I was describing. So here's a shear wall. And if we had a strong foundation and we kind of fixed it and we pushed it sideways, then all of the inelastic action and the damage would tend to concentrate in that stiff shear wall, which is being held tightly to the ground. On the other hand, if we had, kind of a flexible foundation or we modeled the soil, then it's going to rotate almost like a rigid body. Maybe there's some deformation of the wall itself, but you can see how that imposes a rotational demand on the ends of these beams, and these pictures are damaged. This is a stolen completely from ATC 40, which is a great document many years ago that sort of defined the capacity spectrum method. that is now in ASCE 41 as one possibility at least. Okay, so let's talk a little more quantitatively now. And let's talk about, is there some way that I can know before I've, done a whole bunch of work to figure out if I may have benefit or impact from inertial SSI effects. So in that NIST document, this simple equation, H prime over VST, if that's bigger than the number 0.1 was the number that we picked, then if that's true, then SSI effects are likely to be significant, and you probably want to think about doing them. There may be some money to be saved, for example. So what are these? How do you figure out what these terms are? The intent was to make this really simple, and most of it is, but some of it takes a couple more slides. So the effective height of the building is assumed to be 2/3 of the superstructure plus the foundation. Okay, so why 2/3? Because if you took a multi-degree of freedom system and you converged it to a single degree of freedom system in a multi-story building, then that 2/3 is your effective centroid. Obviously, every building would be different from that, but as a rule of thumb, that's what we picked. Then you have to know VS, and I'm going to show you what is VS and how do you get that on the next slides. And then you can use the code fundamental period equation. So as long as you know your system, so hopefully you know what building you're talking about. You may have not have done a complete design or anything, but at least in this case it's a brace frame and you know how tall it is. So you can plug in the CT value and the exponent and the 36-foot height, and you can find out this is a very short, not surprisingly, a very short period building, 0.29 seconds. You plug all these things in, and this just rises above that 0.1 level. So this short building, which before I was involved in this project, it wouldn't have jumped out at me that this thing might have some benefit from this. This is sort of showing, yep, it probably does. Okay, so the VS is kind of tricky though. So where does that come from? So hopefully many of you are familiar with shear wave velocities in general, and know that geotechnical engineers can use those, and the building code has long had provisions to use those to help define the site class of a building. That's moving more and more in ASCE 722 to using that, and less to more traditional techniques like blow count. So VS30 is the average shear wave velocity over 30 meters, or almost the same thing as 100 feet. It is also better defined as the low strain shear wave velocity. Okay, so that means there's something else besides the low strain, and we actually need that. So the effective shear wave velocity uses more realistic strains that happen during earthquake events. And so you have to figure out what is the right VS. So in this blue box, blue boxes are used in our document to kind of highlight things and point out stuff. So this blue box is sort of complaining that ASCE 7 is not entirely consistent, and I would say not all that helpful about trying to figure this out. And unfortunately, it makes a big difference. That these subtle differences are not close to one another. So if you put in VS30 in this building, you would be off by a lot. So 1195 is VS30, 763 is the right number for this test here. So that was cleaned up somewhat, fortunately, in ASCE 722 to be a little more precise in the terminology. But let's sort of do that. So the first thing to do is we need to figure out where's the bottom. So we need to figure out how deep is the foundation. So we're going to talk about that in a little bit later. In this case, we're only going to count the slab because we don't have enough foundation footprint area to meet the 75% test. And so that would be like a mat would meet that easily, or something that has less dispersed elements could meet that. Then we want to figure out something called the effective profile depth. So that comes from sort of the SSI world, and that just depends on the width of the building. So depending on which direction you're going, there's a distance this way and a distance that way. You put it into this sort of cryptic equation, discover it's 31 feet. So you add those two together, it's about 32 feet. That's the kind of the zone of influence that the soil underneath the building where it really matters. If we get a lot deeper than that, it doesn't change things very much. So what we need to do is need to figure out what's the effective shear wave velocity over this 32 feet. So not 100 feet, just 32 feet. Now, it varies with the building, of course, but in this case, that's the number. So what we do is we then go in and we just do a weighted average. So you can see the shear wave velocity profile that you might have in a geotechnical report. If not, you can sort of ask your geotechnical engineer, or you can make estimates drawn to some extent from site class. But in this case, we have this plot. And so we just parse it into its different layers, and we give them a weighted average, and we only go down to the 31.81 feet. So our average low strain, because that's what this thing is actually reporting, is 1,074 feet per second. So we have to ratio that to get it to the effective, the higher strain shear wave velocity that really happens in an earthquake. And that comes from some tables in the building code. So if you know the site class and you know SDS, the short period spectral acceleration, then turns out 0.71 is the answer. So you multiply 1,074 times 0.71, and that is how we got 763. Okay, so takes a little bit of time, but in the end, we sort of figured out, is it worth it to do things on this building? Probably is. That's a pretty valuable thing for a few slides. Okay, so let's now talk in some more detail about our first kinematic technique, so base slab averaging. It's the reduction of demands on the structure due to that variation in ground motion that I've mentioned a couple of times, right? So one of the things that you need to have interlinked foundations. Okay, so we draw some pictures in here, and then they have some descriptions at the bottom, and then I've highlighted in red BSA, meaning base slab averaging. So you may have a slab on grade building that the columns go down to spread footings maybe, and somebody may have put intentionally isolation joints to reduce cracking around those columns. They were deliberately not tying the slab to the columns, and they may have, although in my experience it's a little uncommon, but in this picture A, they may have put in the spreads, water protected the steel column, let's say, on top of this, and then poured back soil on top of that and essentially disconnected the slab from the footing. Theoretically doable. B is what I tend to see more commonly and what I typically personally do. So this is an over pour of the slab on grade. So you backfill, up to the top of the footing, and then you sort of continue. Maybe there's drain rock and a vapor barrier in the middle, and then when you're pouring the slab, you just pour some extra concrete on top of the footing instead of having to backfill on that. And then there's, typically when this is done, there's a dowel, a starter bar coming up out of the footing that goes into this white over pour and then possibly into the slab. So these are linked. So this would typically qualify. There's some mention in the building code and in these source documents about how stiff it needs to be, but typically you're going to meet this. If you have spread footings that are interlinked, you could argue they need to, but you don't have the slab tying everything together. The orthogonal grid, not considered enough. Need to have some diagonal beams to make it more of a kind of like a horizontal brace trim. That would be pretty unusual to actually be built that way. So the extreme and sort of the best version would be, you have a mat that maybe have soft soils and you needed the mat for that's your foundation system. So that's almost always going to qualify. You'd have to have something really unusual like the world's thinnest mat to make that not true. Okay, so if you know that you have the ones where it qualifies, then you just need to know how big your foundation footprint is and what's your effective shear wave velocity. So let's say you had a rectangle that's 100 feet by 400 feet. Then you just put it into this, the area, take the square root of the area, turns out to be a nice round number in this case of 200 feet. That's less than the 260-foot cap, which comes from kind of the collected evidence from past earthquakes that has sort of shown that base slab averaging is true. This is not just a theoretical term. People have empirically collected information. John Stewart, who led that NIST document, that was his PhD thesis, was on this stuff, and ever since, other people have looked at that and have continued to expand the database. But there's plenty of empirical evidence showing that the bigger the building footprint, the more this effect, and the equations kind of come from that empirical work. So we got a 200-foot average effective foundation size. Unfortunately, we put it into some, kind of long-winded regression equation that you want to put in a, spreadsheet or calculator. So when we do that for this building, all we do is we're, put in BE and then whatever our period is on our spectral acceleration. So, if we put it at 0.2 seconds, then we get B naught, we put B naught in here, we get BSA, we put that back in at the top, and you end up with RRSBA. So that's the reduction in the spectral acceleration due to base slab averaging. So that's taking the smooth, solid black line, the red line, sorry, the unreduced value, and then showing that depending on what period you are, it reduces by different amounts. I actually discovered in putting this together that there's an error in this figure in the document that nobody had seen until I just found this week. Unfortunately, it's pretty small. The table where this comes from is correct, but there's must have been some translation issue nobody, including me, caught. Anyway, the point of the image though is the same with the actual number. Instead of 0.8, it's really 0.86 here. There's a issue where you can't go below the reduction from 0.2, but you can see that in this case there's a 15% reduction if you had a really stiff building. But then if you were out here, if you had a really tall building and it was 2 seconds, then this is not going to matter. So this matters. It matters for shorter buildings, but it also matters for higher modes, right? So even if your fundamental mode is 1 second, if you're doing a dynamic analysis and you had higher modes, then they would be impacted by this effect as well. Okay, so now we're going to flip to embedment effects and talk about those guys. So this is about the depth, okay? And it just has this equation. That's all there is to it. So you got to know what E is, and you got to know the shear wave velocity. And then again, you need to know, in order to plot it on a response spectrum plot, you got to, just go through the periods. So part of the trick is figuring out what is E. It sounds like how hard could that be? But because of this need for it to be fairly representative of the foundation footprint and the 75% threshold, we decided to draw a bunch of pictures to kind of illustrate, how that would really work in kind of real foundation systems. So in a mat, it's pretty simple. The depth is the full thickness because it's over the full footprint. Easy one. What if it's this grid here? So what this simple set of equations is it's saying, let's take the footing area, so the gray stuff. So we've got, 6 by 6 square spread footings, and we've got 4 times 4 of them, and then we've got connecting grade beams, and so that adds up to 1584 square feet. The footprint is the whole thing, kind of out to out, and that's the 4104. So 39%, way less than 75. You don't get to count this in your depth. You're stuck in this case with just the slab on grade, which does go over the whole thing. So it's actually kind of a hard test to pass. Okay, so what about this? What if you're, now you have a basement and you go down. Let's say you had that same kind of spread footing base that we just saw. So you would be going down to, actually you should be going down to the bottom of the slab, but you wouldn't be able to go to the bottom of the footing, but you get a full story height. So pretty significant. And it turns out, just due to the limits of what empirically has been collected, there's a restriction in the building code if they don't let you go more than 20 feet down. But a 20-foot E in those equations will lead to significant reductions. So let's do an example of that in a sec here. We've done some partial basements here. Sometimes a building might be on a sloping side, or it might just, only, half of it or 3/4 of it is below grade and the other isn't. So we show you, it doesn't qualify in the one on the left, but it does qualify for that full basement on the one on the right. Okay, if you have a sloped site, of course, there's lots of those, then the recommendation is to use the more conservative value, the one on the left here, not the taller one, and not the average. Interesting, just do the more conservative one. So let's say we had 22, 24 feet here. We would not use 24 because that's the high. We actually wouldn't use 22 either because it exceeds that 20-foot depth. So, in this case, there's enough embedment that we're capped out at the 20 feet. Okay, so let's take that building, let's take that 20 feet and let's calculate the average low strain velocity over that. So again, we have this, we could have a similar picture. I'm just picking this same one that we had before, and I'm taking this down in this weighted average just to 20 feet. So see in the equation down here, 20 minus 9.84, that's because the next layer transitions at 9.84 feet. So this gives us the low strain shear wave velocity, what we call VSO, 972. And then we go into those tables again to have the conversion to get it to the effective shear wave velocity. So in this case, that's 0.687. Multiply those values together, we get 668. We put our depth of 20 feet, we put our effective shear wave velocity of 668, and then we just cycle through and going through different periods. So you can see that at a 0.2 second period, which is a floor, you can't, even though the equations would give you a lower value, it doesn't let you use a value that's any lower than the one you get with 0.2. That's 0.7. So that's a 30% reduction in the short period. That's a pretty big deal. And then it gets less and less as we go longer period. So that effect has been borne out in empirical collections as well. So, we then put that on, here's the black, no SSI, we do those reductions, and here's what that reduced value gives us. We can combine the two effects. So if we had a building that's big enough to qualify for base slab averaging and deep enough to have some meaning, you can actually combine those effects, but you can't make the reduction any less than 0.7. Another one of these sort of arbitrary, sort of don't go any lower than this thing's in the building code. Okay, so next chapter, which I'll just go briefly through these next ones in the interest of time here. This chapter 6 is about soil flexibility. And this, there's no information on how you get anything to be able to do this in ASCE 7. There's a lot of information in all kinds of other places, and we list the NIST document, ASCE 41, the ASCE 41 design guide, that FEMA P-2006, and then our own document here. So we give examples in that chapter of different methods and different values and how you calculate the springs and then what it does. Chapter 7, we go through worked examples of period lengthening. So here's 3 different example buildings: a 3-story concrete building, a 10-story concrete shear wall building, and a 10-story more flexible moment frame building. So you can see how the periods here, 0.2 seconds in our short shear wall building, our taller guy 1.3 seconds, our moment frame of the same height is more flexible, 2 seconds. Okay, now what if we put them on a flexible base? Okay, the spectral displacement as you lengthen the period is always going to go up, but not necessarily the same thing on the forces. So this stiff 3-story shear wall building is actually on the upward side. So it goes from that open blue square fixed base to right at the peak of the response spectrum on the flexible base. On the other hand, the taller guys, where there's shear wall and moment frame, they go down. And you can see how the change is a bigger deal. So the moment frame, which is already pretty flexible, has a change, but it only goes from 2 seconds to 2.4. The shear wall building is more impacted. Again, that's a little bit like that high structure to soil stiffness ratio that we talked about earlier. Okay, chapter 8 is about foundation damping. So, damping, we traditionally have used a 5% damped spectrum to represent the damage and cracking of structural and non-structural elements in buildings. In the superstructure, the soil, we can add to that with this. This is kind of a freebie. And it's not something anybody, I had never done this before on this project, but it's, one of them has sort of easy equations. The other one is fairly involved, but on the other hand, it does definitely make a difference. So CB Kraus, who was on our project team, had pointed this out to us all, that we didn't want to forget about this. It's sort of lesser known, but it definitely can make a noticeable difference in reducing your overall spectrum, not just at the short period range, but the whole thing, because that damping applies everywhere. So you gotta, this doesn't apply to deep foundations. There just isn't a method for that. And there's some other rules that are a little tricky to think through about the nature of the foundations. Okay, so let's move on to a new topic here. Let's talk about basements. So it's a little bit of a whirlwind tour. But in basements, we're going to show kind of simple examples. And I want to point out that one of the really interesting things that the NIST document did is they took some real buildings and that actually had recordings from earthquakes and then modeled them in different ways and sort of ever increasing levels of sophistication. So model 1 is like the simplest one of all, like just fix the bottom and totally ignore what the ground does. So no SSI over there. Model 2 was, well, it's got a basement. Let's act as if the soil above the basement floor doesn't exist. So let's fix it at the very bottom of the basement instead of at the ground surface. Model 4, the bathtub model, was that the bathtub has these springs and dampers that are connected to the building that's inside of it, and you basically apply the ground motions that you may or may not modify to the bathtub, and then you wiggle the bathtub back and forth and the building wiggles around inside of it. Model 4 simplified was a version that in the peer tall building initiatives document sort of applied that in an easier way. The baseline model over there on the right is a very fancy model. So that actually has depth variable ground motions, it has soil damping, it has different springs with different heights, it has horizontal, vertical springs. That would be a pretty rare thing to do, but that was modeled. And so we were trying to see, you know, how closely we got to record motions as well as how close we got to the baseline model with these simpler models. And what we learned is that for moment frame building, both model 1 and 2, so pretty simple models, are good. And for shear walls, this model 4, as well as model 2, work pretty well. So I have sort of typically been doing model 2. I was actually doing it before this project, but I was sort of reassured after we did the NIST work that that was a pretty good idea. One kind of simple thing to take away is if you have a stiff retaining wall, you know, so every basement's got a concrete retaining wall to hold back the earth. So you got kind of a stiff bottom. If you've ever tried to, you know, learn about sort of what is passive pressure as you push into the soil and the soil pushes back, turns out you need a fair amount of movement to fully develop passive pressure. If you actually, you know, got the full value, you know, you're moving an inch or more, you know, and a stiff concrete shear wall foundation would be trashed in order to do that. So in order to actually mobilize meaningfully the surrounding soil in a, you know, situation like this, it's not going to happen. And so that model where you're essentially ignoring the soil is a reasonable approximation. Obviously it's more sophisticated than that, and it's not exactly what I'm saying, but that's one kind of easy to understand reason why model 2 is not so bad. Okay, so let's apply model 1, the fixed base one, and let's think about how you would, you know, how would you figure out the loads on the basement? So this is sort of a 2 model kind of approach. So the first model is the superstructure from the ground surface up. You figure out your base shear, you figure out your story forces. So you can see, you know, 2,000 kips at the roof is our force at the roof level. Then the shear immediately underneath that's the same 2,000. And then by the time we get to the bottom of that, there's 40 kips of shear going through this frame or this building. Then a separate model would say, okay, I'm going to take those loads that come down, both their horizontal and their overturning loads, and I'm going to apply them to a 1-story, you know, shear wall bottom that has its own characteristics and its own shear, and then just linearly combine the 2. Okay, so people have been doing that, you know, for many, many years, and that's how you would figure out what the loads are, both in your basement walls and in your, you know, that ultimately go down to the foundation. You may have different R values, you know, brace frame and a shear wall wouldn't necessarily have the same R, so you have to ratio things by that in order to do that. Okay, another way to do it, this is the model 2. This is where we ignore the soil and make it one model that includes the basement plus the brace frames above. And we run a dynamic model with that. And what you find, and I have done this many times with many different buildings, what you find is when you do that, typically the inertial load from the mass of the shear wall that's tributary to level 1, not much of it goes up in the building. You know, it's kind of a stiff bottom with a more flexible top. It's a podium-like structure. That's what you tend to find. But anyway, we ratio or scale these values so that we take the initial dynamic work where we're getting 3660 as the story shear between level 1 and level 2, and we go to the previous one where the building code base shear is 4240. We multiply the one on the left times that scale factor, you know, 1.16, and then we get our final, you know, 1 model scaled value. And it turns out in these examples pretty close to one another between model 1 and model 2. If we had a sloping site, And this is a sloping site where we model it is this full height single model, and do the work that we had before. And then we linearly combine that with the pressures that the unbalanced soil are putting on the right. So there's a static pressure and a seismic increment or a dynamic increment. It goes by different names, and your geotechnical engineer will be giving you these values and telling you how to combine things and apply them. But typically what we do is we have those as different load cases. So we have kind of the soil pressure load case is one thing. We have the building inertial effects is another thing, and then we just add them together in our model, or post-process it that way. So this is a common way that I have done, and lots of other people have modeled this situation on a one-story hill. Okay, so take a breath. We aren't doing any breaks, but we're now going to move into these two examples that are drawn from kind of more beginning to end, so to speak, where we look at a whole building and we think about how SSI would get invoked in the design process. So like I mentioned at the very beginning, this presentation, due to the interest of time, is just going to cherry pick a few selected topics, but there's a lot more detail and a lot of valuable other techniques and comparison case studies of, if you made this variation and changed this, what would happen? So there's a lot of meat in those two examples that our writing team put together. So this two-story BRBF building, buckling restrained brace frame building, Steve Harris was the primary author on this one. So this covers how do we put in both vertical and horizontal springs. Horizontal springs are a little less common to do, but he kind of walks you through how to do that here. And we show soil damping, radiation damping, and base slab averaging, how that would change things. We talk about the limitations in the provisions, how low can you not go? What can you add together? What can you not? So we try and make this not just theoretical, but practical, and make sure you don't overuse this and miss something that would have prevented you from using the actual number you were calculating. That can be an easy mistake to make, given that there's a lot of kind of overlapping restrictions. So this building in pretty high seismic zone, so it's SDS value 1.57. It's on site class D. So many of you who've used ASCE 7 have probably learned the joys of what happens if you're on site class D or E and trying to figure out how to interpret the building code provisions, which have now gone through 3 supplements to deal with the challenges of interpreting section 11.4.8. This was written while that was happening, and supplements 2 and 3 I don't think existed when we were writing this, but there is a increase when you're on site class D. One of the kind of exceptions you can do is you can extend the plateau over to the right. Why are they doing this? Is because it's been shown in more recent research that on site class D and E, the sort of default spectra that we've been using in the building code don't do a good job of enveloping what actually happens, and unfortunately we're underestimating results. So you're going to see a big change to try and do a better job of this in ASCE 722, but that's a whole nother topic. So anyway, we've drawn this here to show you the extension that you would invoke through that exception. And then the important point here, though, is it doesn't actually matter for this building, because our longest period in any of the variations we study is still up here to the left of the extension point. We're on the plateau, so that it's a really big plateau, and we're on the plateau. So the fact, wouldn't have mattered if we extended or didn't extend it. So here's our building. Some kind of grade beams or mats, whatever you want to call them, underneath the brace frames, then some spreads in between, no interlinking elements, but the slab kind of connects things together. And then it's a steel frame building above with steel columns, steel beams, fill and metal deck, floors and roof, very regular, very orthogonal kind of thing. We've got a transverse direction up and down, north south, where we've got 2 brace frames at line A, 2 brace frames at H. And then in the longitudinal direction, we actually got 3 braces. The base shear is the same. So that means that the sizes in the transverse direction need to be a little bit bigger to take the same force. So our initial fixed base design, in SSI, you kind of always start with the fixed base and you're comparing things against it. So take our, the equations for fundamental period. We got the 25-foot height. We've got our CT value that you would use with the BRBF, and you get 0.34 seconds, very short period. Our R value is 8, not a risk category 3 or 4 buildings. So IE is 1.0. So we get about 0.2 G is the LRFD design value. So we get about 950 kips. So then we could distribute that in this bottom table here to the two lump masses, the roof and the second floor. So we get about 600 kips to the roof, 300 kips below. We've got 2 brace frames, each of which have 2 braces on the left and the right. So 8 total. You compute the vector due to the slope of that brace, figure out what the axial force is in the brace, compute the core area, change it to kind of a nice round number, and voila, that's the sizing that Steve did for these braces. So the foundation, to figure out whether this, mat or grade beam blob here is wide enough into the page and long enough left to right to work, is just kind of an overturning check, and it turns out it satisfies global overturning, has a factor of safety of about 2, and then the bearing pressure that he was allowed is 4.5, and the actual one with the loads on there is 4. So he's got a viable foundation system. He was doing this at the LRFD level. It's a little unusual. A lot of foundation work is typically done at ASD, so you have to reduce your LRFD earthquake loads down to ASD values, but you don't have to. So if you have a LRFD capacity from your geotechnical engineer, then you don't have to do that. So I'm just giving you some sort of highlights of what happened when he went through this, and when he put in vertical springs. And in the building code, there is a requirement to bound the springs. So you have to take your best estimate. In this case, it was 6.94 kips down there in the middle, and take 0.5 of that, 50% of that, 3.47, and then take 1.5 times that, 10.4, and then you gotta run it all with that. So there's a sort of, is that really essential? Unfortunately, in the building code, it makes you do this, and so there's some kind of extra iterations that get triggered because this building code provision. He's also showing you the lateral springs he put in, and then the results, this table on the right. So we're going to focus on the transverse, the one with the 2 braces in the north-south direction of the building. So the fixed base period 0.466, and the flexible base ranges from 0.51 to 0.59. So some increase in that value due to these springs, just like one would expect. So one of the key things that he describes in there is how to apply foundation damping. There's a lot of equations in there to do that, and there's 2 parts to it: soil hysteretic damping and radiation damping. I'm just going to show you the results of those equations. So you're going to get a value for hysteretic damping, which is a pretty easy equation to calculate. A more involved one is to get the radiation damping value. You then combine those guys in another equation. And essentially what happens is you get 0.0 0.46, let's round it to 0.05, is the foundation damping of these two combined effects. The building, we're going to assume, has the traditional 5%. So we're basically doubling in this building the damping ratio. That's a pretty big deal. You know, these numbers seem small, but you know, doubling 5% to almost, you know, 9% is noteworthy. So what does that change? That takes a base shear of 0.196 down to at the best estimate of springs to 0.166. So, you know, pretty noteworthy value. It turns out there's a limit. There's always a limit, and a limit when you go through this other section is, in this case, because the R value is bigger than 6, you're capped at only allowing a 10% effect. So it's a pretty dramatic restriction that you don't want to forget about. Okay, so the last thing, or the second example that we're going to cover here is what was in Appendix B, and this guy has a lot of things in it as well. So he covered this was written by Mike Valley of MKA, and he was talking about both base live averaging and embedment. So those are kinematic effects, and then adjustments from damping as well as period elongation, and also goes through how limits affect us. So what you can see in this model here, moment frames in both directions, and in one direction it's dual system, where you've got walls. Those are the red guys in there in the interior. So it's on site class D. A site specific analysis was done, so you didn't have to do that extension that we had in the 2-story one. This turned out to have these nice round numbers and SDS of 1. So if we look in plan at this building, here's a little maybe easier way to understand. In the transverse left to right direction, we've got a combination of the moment frames, and these are concrete moment frames, and the concrete shear walls. In the up and down long direction, it's just moment frames. So I'm going to have Kiara ask another question here.
Great. So which direction will have more significant impact from soil structure interaction, the dual system direction or the moment frame direction? And we'll give you a little bit of time to think this over. All right, looks like about half of you have already responded. Give you a little more time for the rest of you. And try to get your answer in now. I'll be closing it shortly. 3, 2, 1. All right, Brett, I'm sharing the results.
All right, so we have an 80-20 split here, and the 80%, yes, that is correct. So I was hoping that we wouldn't get 50-50 here, because this is same height, one direction is a moment frame, more flexible, dual system stiffer, has a higher structure to soil stiffness ratio. So that's the one that matters. And the detailed design example totally bears that out. So you guys for listening, and that is the effect. So we actually have 4 different variations in that worked example, kind of showing the influence of a basement or no basement, fixed versus flexible. Starting again with fixed base design, you know, taking the 0.9 second period that's comes out of that equation. There's an upper limit value that's 0.127. That turns out to be less than the computer model period. And this is a very common set of outcomes. You know, this often happens exactly like this. So you actually only get to use the upper limit value here. That's the 1.27. Go through your design equations, discover that it's the velocity dominated equation that governs 0.079. So we got about 3,500 kips of base shear to worry about. So there is a detailed discussion of base live averaging in that guide. There's a detailed discussion of embedment, and you can see the results of these different response spectra of how they drop things down, and then there's some limits that kick in. So for example, In chapter 19, which is where the SSI provisions are, there's this site-specific modified spectrum that was used can't be below 80% of the free field. Okay, so you can only take advantage of a 20% reduction, and then you can't modify your site specific below 70% of the mapped values. So that's to make sure somebody didn't go too far away from what USGS is in there. And then there's a third thing, you can't, the resulting modifiers from those two effects can't be less than 0.7. So we mentioned that before. The biggest thing of all, though, sadly, is this, which is that despite all the things I've been showing you, in ASCE 7, you can only apply these kinematic effects of reducing the spectra when you're doing non-linear response history analysis. You don't get to use it on equivalent lateral force or modal response spectrum. This restriction is not an ASCE 41. So if you're doing a retrofit, you can do all this stuff. If you're doing a new building, then in theory, or at least by code, you only get to use it for the few buildings that are being done right now with NRHA. He goes in detail and talks about period elongation and shows the results of that. That's important because that leads us to being able to account for foundation damping. You need to understand the difference between the fixed and flexible base periods to plug into these equations. You don't get to use radiation damping on deep foundations. So in this case, we had 5% for the building. We're only going to increase that to 0.064. So this is less significant for foundation damping than it was for the two-story building. So when we go through these, plug it into those values, then you can see the difference is not all that dramatic in the final value. So the limitations matter. It turns out, ironically, in the north-south direction, there's yet another rule in ASCE 7. This doesn't have anything to do with SSI. It's the floor. So that building was tall enough that the low bound on your base shear equation actually governed, and that's so don't waste your time in that one if you realize early on that that's actually your situation. So I don't want to go through all these numbers, but I just wanted to point out that since we did all these flavors, so we did things for the 4 different models, we did things for 3 different values of spring stiffness, and depending on which restriction you apply or don't apply, you can get a pretty big range of values of the ratio of the base shear with SSI versus not with SSI. You can always get this 10% value, but you could have, in some cases, you can go as low as almost half. It's pretty dramatic depending on the situation that you have. Okay, so I'm going to skip this one, Kiara. I'm going to tell you the answer to this. So which of these is more conservative? ASCE 7 is more conservative than ASCE 41. And here, this table, which you can look at in the design guide, kind of goes through a cross comparison of these different standards from a whole bunch of different issues, like which site classes can you use. Turns out you can't use SSI on site class A and B because it won't do much for you. So when you're on rock, that you don't have that flexibility of the soil, and it doesn't make much of a difference. So they don't even let you try. But if you had tried, you would find out it's not gonna matter. So the building code is ironically kind of saving you effort here. That big issue that I was pointing out about when can you use base lab averaging and embedment, that's summarized here, and there's a difference between the two. These floors, how things need to be connected, what the restrictions are in some situations. Sometimes they're identical, sometimes they're not. So you got to be careful. If you're in a retrofit and you're using ASCE 41, that's what's permitted by the authority having jurisdiction, then you're in one kind of realm. If you're a new building and you're using ASCE 7, then you've got a different set of requirements. Okay, so I'm going to wrap up here, and we should finish on time or a little before, I think, with some takeaways. So I have more than 3. So the rule of thumb is, don't give people more than 3 things to take away, but you're all engineers. So here we go. First thing I want you to realize is it's not that hard. So years and years ago, my impression was, wow, I saw all these big long equations that, to calculate springs, and it looked kind of daunting and painful, and nobody was doing it. And that's really not the case. So it's changed. It's easier to use, and hopefully this design guide and other resources will make you realize that it's not as tricky as one would have thought. It is typically iterative, so you need to, in a fixed base design, it's just fixed, so there's only one permutation. But in a flexible base analysis, you might have to iterate a couple times until something converges. So that takes more effort. So I'm not trying to claim that this is so easy that it's equal to fixed space. That's not true. It's definitely more work. It usually reduces seismic demands. There is that situation I showed you where you climb up the response spectrum and things can get a little longer, and then you can go up from near the plateau on the left short period side of the response spectrum. A big thing is adding in that flexibility can really change the way things move. So I showed you that example was on the opening slide, and then that worked example that we had done in the ASCE 41 design guide, where the brace frame, kind of converted from one mode to a totally different failure mode, depending on whether we did or didn't have foundation flexibility. It doesn't always happen like that, but it's something to be aware of. There are situations with these concentrated shear walls or brace frames where that can be particularly true, and important, because you may be, misleading yourself into thinking about what's really happening if you're just doing a fixed based analysis. You got to know which shear wave velocity you're supposed to be using. As I explained, there's all these different terms, and they're not always as helpful as they could have been. So we talk about this in great length in the design guide. Hopefully we make it clear and tell you exactly which one to do and how to do it. Lots of limitations, provisions to watch out for, and then ASCE 41 generally has more relaxed requirements than ASCE 7. So I will turn it back to my colleague Kiara here.
Great, thanks, Brett. So on behalf of FEMA and the Applied Technology Council, I'd like to thank Brett for his presentation, and also thank everybody in the audience today. We did have a record number of participants at 1,700. So really happy to see the interest in this topic, and appreciate your patience with the issue that we had with the handout link. There were so many people interested in SSI that you broke our website, which is an honor, I think. And not really the website, just the link. So for those of you who are eager to receive your PDH certificate, note that they are only provided if you both registered and participated in the live webinar. So if you are watching this in a recording, you are not eligible for a PDH. You can expect your certificate within the next 4 weeks. And please understand that due to the large volume of participants, we cannot make exceptions to our PDH policy. If you have a question for Brett that you have not yet submitted, you can go ahead and type it now into the Q&A. We'll leave the webinar open for a few extra minutes to give you some more time to craft a question if you have one. And answers to the questions that will be written by Brett will be provided by email within the next 4 weeks. Please click on the survey link that pops up when you leave. We especially appreciate your input on the topics that you'd like to see in future webinars, because we certainly review that information closely when we're planning our program for the future. Lastly, you can expect a follow-up email in the coming days with links to the recording, to the handouts, and then also to the survey again. So this concludes the webinar on FEMA P-2091, and I hope you have a great day.
Thank you all.
Thanks.